After learning about standing waves on strings, the other type of standing wave that will talk about when we look at musical instruments are standing waves in pipes, okay? And I'm sure you've all experimented with blowing air over top of a bottle. It'll make a sound like this. And that's formed by a standing wave or a standing longitudinal wave being formed inside of the bottle. So you're going to be blowing air over top, which creates a vibrating pressure inside of that bottle, and the air is going to form a longitudinal wave that's going to travel down and bounce off that boundary and back again. And that reflection is going to cause the waves to superimpose and create a standing wave like we learned about in the strings. Okay, and we have two different types of pipes. You can have a closed-ended one where you have a boundary on the end, and then you can have an open-ended pipe where there's two openings. And when you blow air across that, it also makes a sound, but in a different way. The frequency would be different, okay? So the same rules apply. In order to create a standing wave, you need a reflection, and that reflection superimposes the wave back on itself to create a standing wave, okay? So we're going to be talking about the physics of open-ended waves and closed-ended waves as we go along. Let's start with the closed-ended pipe, okay? So when we blow air across that open end, you're going to cause resonance, okay? So the air molecules, which there's lots of air molecules all the way throughout this pipe, those air molecules are going to be pushed in and out. That's a double-headed arrow over there. They're going to be pushed in and out with a frequency. And as long as that frequency is set appropriately, what you can create is a standing wave, and you're going to make that sound, all right? So the simplest standing wave that would be made is if the wave reflects off this closed boundary and comes back on itself. Now remember, when a wave reflects, when these particles are pushing and sending that longitudinal wave and reflecting off of that boundary, whenever a wave reflects, it then changes its phase, and we will get what's called a node. So I'm just going to change the color here. So I will have a node, okay? I'll have a node formed at that closed end. So the simplest wave that we would make is a node over here, and then all that would look like that, okay? And then at this end over here, I would have an antinode, okay? So an antinode is formed wherever you have an opening, all right? Because there's nothing for that wave to reflect off of. So you always have an antinode at the openings of a tube, and you have nodes at the closed end of the tube. So a good way of looking at that is right here. This is the same as this. You have an antinode at the opening of the tube and a node at the closed end of the tube. So if you look at the wave that's formed, that wave, or the length of that tube, okay, L, that wave is a quarter wavelength, all right? A full wavelength would be 4 of these, where it goes like that. So that standing wave that's formed in the closed end is a quarter wavelength. All right, the next type of wave, or the next harmonic that I can form, remember I always form a node over here, and I always form an antinode over here. So the next type of wave that's going to form, okay, I have to end with an antinode, okay, would be that. So again, I'm ending always with an antinode and ending with a node. That would be the next possible variation. So in that case, the next harmonic would have a length. The length corresponds to 3/4 of a wavelength, okay? And then you can see the next variation, where I always have an antinode at the open end and a node at the closed end, would be a full wavelength plus a quarter, so 5/4 of a wavelength, all right? So if I wanted to come up with a formula for the wavelength of a standing wave in a closed-ended tube, the wavelength is going to be equal to 4 times the length of that tube. Oops, the length, that's my length. So 4 times the length of the tube divided by n. And if we take a look at what n is going to be equal to 1, 3, 5, and so on. They have to be odd integers, because that's the pattern that would have to fulfill the requirements, where an antinode is being placed at the open end of the tube and a node is being placed at that reflective boundary. Okay, so what can we do? With this formula, I would be able to then start to calculate what frequency that tube is going to make. What frequency is that? And that frequency is dictated by the length of the tube. So the length of the tube, L, would allow me to calculate the simplest wavelength. Now the simplest wavelength is when n is going to be equal to 1. All right, so that formula here would allow me to calculate the simplest wavelength, and as long as I knew what the speed of that wave is traveling in here, I'd be able to calculate the frequency. So what's that speed going to be? Well, that speed is the speed of sound traveling in air. Okay, so then the velocity is equal to around 340 meters per second. That's the speed of sound in air. Okay, and we can change that speed based on temperature if we wanted to. So let's go take a look at a practice problem. As long as I know my velocity and I'm able to calculate my wavelength, I can then calculate the frequencies. So the first question is, calculate the fundamental frequency produced by a closed-end pipe that's 50 centimeters long. So let's imagine that L is 50 centimeters. So the first thing I'm going to do is I'm going to calculate the wavelength. Okay, so if I have a 50 centimeter tube, okay, that wavelength that's going to form is going to look like that, a quarter wavelength. So again, my wavelength is going to be equal to 4 times L over N. And in this case, the fundamental frequency, N, is equal to 1. Okay, so my wavelength is going to be 4 times 0.5 meters. Remember, I got to use SI units. So my wavelength is going to be 2 meters long. Okay, so that 2 meter wavelength that is going to be formed inside of that tube, what frequency is going to be produced? Well, now I have to use the wave equation. So the speed of a wave is equal to the wavelength times the frequency. So if I rearrange that equation, the speed of the wave divided by the wavelength is going to be equal to my frequency. Okay, and we know that that speed is going to correspond to the speed of sound. So 340 meters per second divided by 2 meters gives me a frequency of 170 hertz. So after calculating 170 hertz as the frequency that would be made by that pipe, let's take a look at how we can calculate some of the harmonics. Okay, so if we go back here, these are the harmonics. So let's look at the next harmonic. This harmonic is called the third harmonic because n is equal to 3. Okay, and you can see that the harmonics skip. I got a first harmonic, a third harmonic, and a fifth harmonic. That's very unique to closed-end pipes. There's no second and there's no fourth. It's always odd integers. So the next question says, calculate the third harmonic frequency produced by a closed-ended tube that is 50 centimeters long. The easiest way to do this would be to take 170 hertz and then just multiply it by 3, because that's what the formula says. Okay, so I would be able to just take 170 hertz times 3, and that would give me the third harmonic frequency. But I want to take it slow, and let's just work ourselves backward, because it's nice to practice that equation. Okay, so remember, first we got to do is we got to calculate the wavelength associated with the third harmonic. So the wavelength is going to be equal to 4 times the length of the tube divided by n, which is going to be 4 times 0.5 meters divided by 3, okay, which is going to give me something like 2 meters divided by 3, which is equal to about 0.66 repeater meters. Okay, so that's the wavelength that I have. And just like we did above, in order to calculate the frequency, I just have to take the speed of sound divided by that wavelength that I calculated for the third harmonic frequency is going to give me that frequency. So 340 meters per second divided by 0.66 meters per second should give me 3 times that value. Okay, so 3 times that value is going to be equal to around 510 hertz. Okay, which is a larger number. All right. So now what do we do about open-ended pipes? Okay, so an open-ended pipe, we don't have an actual boundary on either end. So how do we make a standing wave if there's no boundary to reflect from? Well, actually, you're going to be reflecting from the edges here, or the air. It can even reflect from the change in the medium, from change in pressure in the air. So you do get some reflections, but because these are 2 open ends, the wave that's going to form, I have to have, let's just change the color here. I have to have an antinode at both of these places. So I'll have an antinode at that opening, and I'll also have an antinode at that opening. So the standing wave that's going to form with the air molecules, I'll have an antinode here and an antinode here. So in order to create a wave pattern, the simplest wave pattern that can be created would look like this, where in the center, I'm going to have a node. Now, something that's interesting, when you create a longitudinal wave with air and a standing wave and a node, these air particles, those air particles over here at the node, I'm just going to draw these little air particles, they're not moving. And what that means is that the pressure over here at a node is going to be zero, low pressure. There'd be no pressure there whatsoever. At the antinode is where the particles are going to be moving the most. So at that place, I'm going to have high pressure. And over here, I'll also have high pressure. So if I had pressure sensors in there, you'd be able to sense where the nodes and antinodes are. Right at the center, at that node, I would have no pressure whatsoever. Okay, so just like in the other examples, I will have a length, and that length is going to correspond to a wavelength. Now we can map this out. The wavelength of that standing wave formed inside of that open-ended tube looks a lot like half a wavelength. All right, if I put those together, head to tail, it looks like half a wavelength. And you can see that here, that the length of that tube corresponds to half a wavelength. The next harmonic, now remember I always have to have antinodes at the end, so I have antinodes at the end. The next harmonic that I can make has two nodes inside, and it looks something like this. And then the next harmonic would have three nodes inside, so one node, two nodes, three nodes for the harmonics. And if we take a look at the next one, for the next harmonic, I have the length of that tube is equal to one full wavelength, and the length of this tube is equal to 3/2 wavelengths. So if I wanted to recreate the formula, the wavelength of a standing wave in an open-ended tube is going to be equal to 2L divided by N. That's the formula. And in this case, N can be any integer whatsoever. So I would have a first harmonic, a second harmonic, a third harmonic, and a fourth harmonic. Okay, I can put that in for N, and I'd be able to calculate the wavelength of a standing wave inside of a tube. So how do we use this? Okay, let's imagine again that this tube here is 50 centimeters long, and let's go and calculate here. Calculate the third harmonic frequency produced by a 50 centimeter open-ended pipe. Okay, so if I drew the pipe, okay, the third harmonic frequency would have three nodes inside. Okay, and it would look something like that, I believe. Yes, that's our third harmonic. Okay, and the formula says that the wavelength, I'm just going to change the color of the pen here. Okay, the wavelength is going to be equal to 2L over N, which is equal to 2 times 0.5 meters divided by N, and in this case, N is going to be equal to 3. Okay, and so for that third harmonic, my wavelength is going to be equal to 1 meter divided by 3, which is equal to 0.33 repeater meters. And then to calculate the frequency that would be generated, I got to use the wave equation again. Speed is equal to lambda times frequency. And remember, the speed of the wave is going to be the same as the speed of sound. So 340 meters per second divided by 0.33 meters is going to give me my frequency, which is going to be equal to basically 340 times 3. All right, so 9, I think that's right. I'm just doing it out of the top of my head. I'll have to calculate that later on, but around that. So you can see that the frequency generated by this 50 centimeter pipe is different than the frequency generated by the closed-ended pipe. Okay, if I go back up to the closed-ended pipe that was the same length, here we go. Oh, we found out that that third harmonic frequency is 510 hertz for a closed-ended pipe, and the open-ended pipe is going to make a higher frequency sound. Okay, so the closed-ended makes a lower frequency, the open-ended makes a higher frequency sound. And that's basically how we do our calculations. I'll be giving you a worksheet to go through all these calculations and apply the formulas. Just as a rundown, in order to be able to calculate the frequencies, we first have to be able to calculate the wavelength that is formed inside of that open or closed-ended tube. And once you've calculated your wavelength, you can then use the wave equation to calculate the resonant frequency that forms. Okay, if you find the fundamental frequency, you can multiply that by whatever harmonic to quickly get the answer for what the harmonic frequency is going to be.